understand the underlying significance of the problem. It is not like, just like a robot that you are seeing the solution and you are just trying to memorize it. It's not like that. You have to understand the inherent philosophy inside the problem. Then only you would be able to answer questions in the exam. Okay, so you have to understand the problems very well and practice it obviously very well. And the lecture notes, you go again and again and again. Maybe first time when you go through the whole lecture notes, it will take like maybe 7 days. Then the next revision when you do, it will take maybe 4 days. Then the next revision, it will be maybe 2 days. Like this, you would be able to revise the whole lecture notes in 1 hour maybe. So it is like that. So you have to 4 or 5 times before the exam, you have to go through the whole lecture notes, right? So that you can revise it within an hour. You understand what I mean? Because more and more you practice, it becomes easier for you, and the time taken to revise the whole syllabus will be lesser. So within 1 hour, you would be able to complete the revision of the whole syllabus. Similarly for the problems also, you have to go through the problems again and again, do it again and again, so that you understand what it exactly means. So everybody entered? 3, 4, 5, 6. So everybody entered. So did you all understand what I mean to convey? Did you all understand?
Yes, sir.
Yes. So all of you are practicing. Just tell me an yes if you are all practicing very well and everything is okay with you. Everything okay with you?
Yes, sir. Everything is okay right now. We are not too much into this exam. Just gate is also going on, so it's going on simultaneously.
Okay. Okay, but so you can specifically, if you have some problems understanding any concepts or the problem, just let me know.
Okay, sir.
Okay. Otherwise, it will be very. It will be very. What?
Sir, we have
What did you
problem
say?
cell model, sir. No problem
Oh, okay.
related
So
to
you have problems. So you have understanding how these levels are generated. Is that right?
some things I'm not understanding that how we are feeling those things. For example, if you question is asked that find the ground state, spin and parity of any nuclei. So how to do that? So can you
No,
repeat?
actually, those are yeah. So basically, so this shell model is an independent particle model, right? So what I said is that you can consider these all. I mean, you can take one nuclear, and that nucleon you place in the potential of all other nucleons, right? And then when you solve it, you get this spectra that you say that I showed. Okay, so let me go. Okay, let me before starting, let me, if you have a problem, so let me go back to that shell model picture, so that will be easier. Or what I can do is that, let me, since this I open because this takes time, so let me, because we are almost completing the syllabus, so let me finish this and then I come back to your shell model, right? Is it okay?
Yeah, it is okay.
Yeah, because otherwise, because I have already opened this, like, so I have to go to that other file to open that. Let me open that shell model picture, then it is easier for you to understand what I mean to say. Okay, so regarding nuclear reactions, so we started with nuclear reactions in the last 1 or 2 lectures. So basically you can say that there are 2 types of nuclear reactions, which is a fast nuclear reaction and there is a slow nuclear reaction. The fast one is maybe 10 to the minus 22 or 10 to the minus 23 seconds. So that is actually the nuclear transit time. So basically when this projectile is coming and the time it takes to pass the extent of the nucleus, the target nucleus, that is actually the transit time. That is maybe like when we are moving in a train. So you have a station coming up. Now there is an extension of the station. Maybe that is 500 foot. Okay, 500 feet extension. So when the train is going, without stopping there is certain amount of time, maybe 1 second or 2 seconds for the whole train to move through the station. So it is is like that the projectile is coming and there is this target. There is a finite extension of the target. The time for the projectile to pass the target is actually the nuclear transit time. So in direct reaction, it is like 10 to the minus 22 or minus 23 seconds. So within that time, the projectile interacts with the target. Now, usually, this fast reaction, what happens? It is forward peak. That means more and more number of reactions will occur in the forward angles, okay, than the backward angles. So it is very fast. And also, if it's very distant, so it will go to forward angles, okay. And if it's very close to the target nucleus, that is the impact parameter, as I said, the distance, perpendicular distance between the projectile and target centers. If it's very small, then it will be scattered at a larger angle, so interaction will be more. Yeah, but if it's almost, I mean, the impact parameter is very, very small, then it collides head on, right? So it may get backscattered or it may be absorbed by the target nucleus to form a compound nucleus. So then what happens? That projectile becomes a part of the target, so they become a family. And then since this momentum brought in by the projectile is absorbed by the nucleus, the residual nucleus, or I will say the resultant nucleus, becomes excited. So you can see there is this semicircular black semicircles, which actually means that it's excited. So this nucleus gets excited and it vibrates and rotates, and then it starts emitting particles. Now in this case, what happens? There is no memory of who was projectile and who was target. All gets mixed up and becomes a resultant nucleus. And then it emits a number of neutrons or even fission fragments, many things. So you see, in this case, since it does not have a memory, this second figure, the lower figure, the red line, you see that it is symmetric about 90 degrees. So in this case, it's symmetric. Whereas the upper figure, you see, it is more and more counts in the forward angles. The x-axis is theta center of mass, so its forward angles more and more counts, larger angles less and less counts. So direct reaction, most of the direct reaction will occur in the forward angles. And the compound nuclear reaction will occur all over theta center of mass, with the minimum at 90 degrees and both the sides it increases. Okay, so it is clear, this direct reaction and compound nuclear reaction. Main thing is the timing. So you see, compound nuclear reaction is very, very slow. Okay, you might think that 10 minus 20 or 10 minus 16. So this is fast, but fast with respect to what? It is slow with respect to the direct reaction. Direct reaction is even faster, 10 to the minus 23. So you can immediately see at least 10,000 times slower, this compound nuclear reaction. Okay, so it will emit mostly neutrons, then fission fragments, many other things it will emit. Okay, so some kinds of nuclear reactions we already discussed in the last lecture. In the elastic scattering, the entrance channel and the exit channel are equal. So that is, whoever was the projectile, the ejectile is the same. So small b is equal to small a, and whoever was the target nucleus remains as the same residual nucleus. So capital B equals capital A. In elastic scattering, what happens? In the exit channel, that is the resulting channel after the reaction, there are two particles. Say, for example, if it's a two-body reaction, so it's two particles. One is the ejectile, small b, and another is the residual nucleus, capital B. So if the residual nucleus gets excited, that is B is equal to A star. Star means excitation. And also the ejectile is also excited, that is small b is equal to A star. Then we say that is inelastic scattering. Now, it does not necessarily has to be both the ejectile and residual nucleus had to be excited. It may be if one of them is also excited, then also it's called inelastic scattering. Now, if there are altogether new particles emitted, now these are all direct reactions, so these are very fast. Now, if there are altogether new particles emitted, then that is small b is not equal to small a, capital B is not equal to capital A. So that means there are new particles that are emitted after the reaction. So then it's called transfer or rearrangement reactions. So now in this case, also you see two particles in the initially and two particles finally. So initially small a, capital A, finally small b, capital B. So these are called transfer reactions. Now there can be breakup reactions also, where you have initial two particles and in the final state you have three particles. That is, the projectile breaks up into two particles and the residual nucleus remains as the target nucleus. So that may be so there are different possibilities for these nuclear reactions to happen. And for just to start up, I am just mentioning only few of them. So there may be deep inelastic scattering, that is it's inelastic excitation, but it's a lot of involvement among other nucleons inside the nucleus. And obviously you can see there is compound nuclear fusion, that is head-on collision, and then it becomes a part of the nucleus. And this figure, as I mentioned, that if you plot in the x-axis energy per nucleon, that is how much momentum this projectile brings, and in the y-axis is the impact parameter. So it is how far the projectile is there when it interacts with the target. Okay, so if it's very far away, so since the nuclear force is short range, is very far away, then mostly it will interact with the target nucleus through the Coulomb force. It has to come at least close to the nucleus to actually the nuclear force to act. Okay, so this Coulomb force also can cause excitation in the nucleus, and all these things can happen. So you see very high impact parameter is elastic scattering, and if it's very low impact parameter, you see there is multifragmentation. And as the energy increases, first it's fusion evaporation, that is it fuses and becomes a compound nucleus, and then the particles are emitted. And if the energy is far more, then there is multifragmentation, that is it hits head on and it breaks into many fragments. You understand that if there is a big glass ball, and if you hit it with a small iron screw, say, just a small iron bullet, or not bullet, iron screw, or some small iron ball. So if you hit with the small iron ball with this large glass ball, it will break up into many fragments. Okay, it's like that. Now, this also I showed previously. How does it look? So fragmentation is, you can see that it brings in lot of momentum. It's a higher energy particle, and it breaks the nucleus into many fragments. And there are some simple mathematics about impact parameter of nuclear scattering. So you can see that small b, that is called the impact parameter. So it is the path of the projectile, and you draw an imaginary line through the center of the target nucleus. So the perpendicular distance, that is small b, that is called the impact parameter. Okay, you understand what an impact parameter is? Did you understand?
Yes, yesterday we did problems together.
Okay. About on impact parameter?
Yes, sir.
Okay, good. Okay, now there is also some little bit of mathematics which you might require. It depends on this geometry. So if you go through this geometry, there may be a little bit of problems which might ask you what is theta phi, and what exactly is this. There you can understand this is a symmetry plane, and then after scattering it goes in which direction. So these are just a little bit of mathematics. That is the main only conceptual thing here is the impact parameter, and also the distance of closest approach. So you can see when the projectile comes very close to the target, so it actually deviates through its path, and then the point at which the projectile is closest to the target nucleus, that is called the distance of closest approach. So these are the two main things, conceptual things in a nuclear scattering. One is the impact parameter, and another is the distance of closest approach. Okay, and so here you can see determining impact. So you can see the closest approach R minima, and the impact parameter is small b. So you can have this expression. So the impact parameter is a perpendicular distance to the closest approach if the projectile were undeflected. So this actually is deflected. So R minimum is slightly larger than small b. But if it would have been undeflected, it just goes through this dotted line, then that is called the impact parameter. Okay, now obviously you have studied this potential scattering theory in your quantum mechanics too, right?
Yes.
Did you do it? Yeah.
Yes.
So I will not go into details, but what I would suggest that there are just few slides. So you just go through the key expressions. Obviously, nobody is going to ask you to deduce all these expressions during your exam, but if you go through the main key expressions, it will be easier for you to understand what is going on. So you have, you have a target nucleus and you have a projectile, incoming projectile. So you can, if it's very far away, you can take it as a just plain wave. Okay, and when it comes close to the target nucleus, it gets scattered. So you have a scattering amplitude f theta phi, and it becomes a spherical wave basically. So the resultant wave in the exit channel you can take as a summation of the incoming e to the ikz plus a scattered wave f theta phi e to the ikr by r. So you have an incoming plane wave and an outgoing spherical wave, and you have a scattering amplitude f. Okay, and ultimately you get a cross section that is d sigma d omega. You understand because we have schematically studied what a cross section is. So you have this cross section d sigma d omega, that is the number of particles that is falling in a particular solid angle. That actually is the scattering amplitude mod squared. Okay, so you usually we solve the Schrodinger equation in this case, in this potential scattering. So you can get this expression as the solution as the plane wave plus the spherical waves generated by the potential generated by the target nucleus. And you have the scattering amplitude f theta phi can be given by this expression, where you have this incident this plane waves e to the ikr, and this psi k r prime is the resultant spherical wave. So you have this bracket, you can say in Heisenberg notation or in Schrodinger formulation, you have this integral. If you solve it, you get the scattering amplitude f theta phi. Okay, so and you have this Born approximation that you understand that if the scattering wave has small amplitude, it can be replaced by the first term, that is the plane wave. So you can do it as e to the minus a k prime dot r prime, the potential, and then e to the ik dot r. Now you have to appreciate that this elastic scattering, first thing is that mostly whatever the incident beam of particles, only a very small fraction, a negligible fraction interacts, because most of them goes undeflected without even interacting, because the atom is mostly empty and the nucleus is so small that most of the beam particles, they don't even interact with the nucleus, they just go as it is, so they don't interact it. Now out of a negligible fraction of the beam that actually interacts. Okay, and that interaction gives some cross section. Now in among the cross section, the 99% is elastic. Okay, so mostly the incoming particle and the outgoing particle are the same. Now rest 1% is maybe inelastic scattering, breakup, transfer, and all those things. So you can actually neglect all those reactions as compared to elastic scattering. But there is a catch. In the forwardmost angles, the elastic scattering is orders of magnitude higher and all the reactions are very small. Now as you move towards higher angles, then the elastic scattering actually reduces, and most of the flux then goes from the elastic channel to the transfer channel. So as you go increase the center of increase the detection angle, that is the theta center of mass, you will see more and more counts for coming from these other reactions coming up as compared to elastic scattering. Now is this clear? Because in the forwardmost angles you will find mostly it is elastic scattering. Now as you go towards higher and higher center of mass angles, you will see elastic scattering contribution becomes lesser and lesser, and transfer, breakup, all those reactions, they become increasing, they increase more and more as we go over higher angles.
Right.
Is it clear?
Yes.
Yeah. So because you can understand that if the impact parameter is larger, it will be mostly elastic scattering. Now if the impact parameter is smaller, then it will be deflected in a larger angle, and then it is able to interact with the nucleus in a much larger way. And then what happens, not only elastic, there will be other reactions coming up. So you can physically you can understand that as you go over higher angles, that comes from more interaction with the nucleus. So there will be complicated reactions happening, not very simple elastic scattering won't be happening. Because if it's going very far, impact parameter is very high, it is going very far from the target nucleus, then mostly it will be elastic. As it comes closer and closer to the target, more and more interaction with the target, and different and complicated reactions will take place, like breakup nuclear reactions, transfer reactions, inelastic scattering, transfer rearrangement. There are many different types of nuclear reactions that might occur. Okay. And there, the foremost approximation is you can consider it to be a plane wave, that the contribution from those other channels, except for the elastic other channels, you can consider to be neglected. And the first approximation is consider them as plane waves, and the next approximation you can consider them as distorted waves. That is the distortion actually produced by that potential. So you can consider those waves as distorted waves, not the plane waves are distorted. So you can consider them to be the wave function due to the elastic scattering. So it's chi elastic, and then the potential, and then chi star chi, and you sandwich the potential between there. So first is the plane wave Born approximation, and then comes the distorted wave Born approximation. Okay. And I mean, these are actually very lengthy, these require very lengthy discussion, so I am going schematically, so it is very difficult to discuss the details. So you already know these things. So you can consider the wave function to be a summation of different angular momenta. So it is like you can factorize them for different partial waves, so which have different angular momentum. So if it's going very far away, so that has some kind of partial waves, and if it's going very closer to the target, it has a different partial waves contributing. So you have a series of partial waves that is existing. Now it is up to you at what impact parameter this projectile is coming, and how many partial waves you will consider to consider all the nuclear reactions that is taking place. So if you see these schematics, because I'm trying to give you a picture schematically, so you see if there is no potential, okay, so this is the phase shift, the first figure. So you can see this figure, page 170.
Yes.
Illustration of phase shift, you can see it. Okay, so if there is attractive potential, that will pull the wave function. So you have a delta, negative, so it will pull the wave function. But if there is a repulsive potential, it will actually push the wave function. Phase shift. So either it's minus delta or plus delta. That causes a phase shift to the wave function, right? So due to the potential, due to the existence of the potential, the projectile's phase, phase of the wave function that changes. So if it's a attractive potential, the phase change will be something, and if it's a repulsive potential, it will be different. So it is plus delta. So it actually pushes the wave function. And in the other case, if it's attractive, it pulls the wave function towards it. So you see there is a change of phase. Okay. So this is for a particular example of carbon plus silicon. You have these eta L values, and then this as in the x-axis, the number of partial waves that has been plotted, like 10 or 50 or what. Now, all these things there are certain, if you are working in nuclear reactions, so there are certain standard codes are there. So you have to you have to incorporate certain parameters, input certain parameters in those codes to get the cross sections, right? There are DWBA codes available long back that has been developed maybe 50 years back. And these are still used today and these are all in Fortran, because it is not yet possible to convert all those codes into C++ yet. And the issue is that those codes in Fortran, they have been tested in so many times that those are almost foolproof. So we are very comfortable using those codes. Know that there are many things have happened on these codes, and we can input certain things there and get the cross sections from those codes. So, and then experimentally we measure the cross sections, and we try to fit those cross sections with our existing codes. And if there is, so basically experimentally you have to measure the cross sections very accurately. Now, if you more and more accurate measurements, that actually helps the codes to develop also. So the inside the codes there will be updating different equations so that you get better and better results. So you have some DWBA codes with which you can get the cross sections. Now usually I teach another thing after this lecture, so that is interaction of radiation with matter. So I will think it over whether I'll just go I'll discuss this thing. Maybe if it's possible, that maybe in the next lecture I will, because it is even a big lecture. So usually I give it in the this what is called this winter school in astroparticle physics. I give this lecture. It is better to know this, to study this also, because this is also part of nuclear physics. And if you have to study experimental nuclear physics to understand how these detectors work, so you have to understand how the radiation interacts with matter. Now radiation means both charge particle and neutral radiation, both gamma ray charge particles and neutron radiation. So I will see that if I give a lecture about this on the next lecture. So I think that's it for now for the nuclear physics course. Now I will go back to your shell model and all this stuff. So we will try to I'll try to give a brief overview about this interaction of radiation with matter in the next lecture, and I will also discuss all your difficulties and whatever questions that you have. Now one of you have said that you have a problem with shell model. So let me go back to shell model first. Let me go back there. Where is this lecture one?
In 97 page, sir. 90, sorry,
Okay.
4 page.
Okay. Okay. Can you see anything in my screen?
No, radiation with
Okay.
matter.
Okay. So I have to change. I changed it. You are presenting. That presentation is not. So did you enjoy the whatever in nuclear physics that we discussed?
Yes, sir, very much.
Okay. So it is actually best thing is to have a face-to-face interaction. But since this is the first time that we are doing it online, so at some points it is difficult to convey, because like in physical classes, if I want, I could have written something on the board to make you understand better. So there is
Yes,
some
sir, yes, sir.
limitation here through online things, but I am trying my best to make you understand. So we'll just go to 97. Okay. So before going to 97, I'll just tell this thing. So you understand that, as I say, the nuclear shell model, it is a mean field model. So what is a mean field model? So what happened is that there are several nucleons there. So maybe in lead nucleus there are 208 nucleus. So it is obviously not possible to solve this many body problem, quantum many body problem, through using Schrodinger equation. It's not possible. So what we do, we resort to some approximations. So what is this approximation? So what we do is that we try to find out if there is one nucleus which is one nucleon which is outside the closed shell. So there are levels, and there are most of the nucleons get paired up, and there are one or two nucleons remaining which are not paired up. So what happens, the property of the nucleus becomes the property of that particular single nucleon. So what you do, you remove all the other nucleons as a potential, and you put that outermost nucleon, that which is unpaired, you put that nucleon in a particular potential well. Now you are very for a square well, so you just solve the potential well problem in quantum mechanics, and what you get these quantum numbers. You quantize it and you get the quantum numbers. So those quantum numbers are in page 97. Those are in the leftmost this.
Hello, sir.
Hello, sir. Sir, your voice is not coming. Hello.
Can you hear us, sir? I think there is a power cut.
Can all of you see?
No,
No,
sir.
sir.
Hello?
No,
Yes,
no.
sir.
Yeah, so yeah, my network got disconnected. So anyway, I'll again present this. Sometimes this BSNL causes problem. Can you see it now?
We cannot see. We can see your screen.
You can see the shell model screen?
Yeah, we can see the skin, but not the presentation.
Yeah, but the shell model, can you see it?
No,
No.
sir.
Okay, so I'll stop presenting and then again I'll there is some problem. Stop presenting. Okay, I stop presenting and then again I will try to present. Yeah. Oh, can you see it now?
Yes.
Yes, sir.
Yeah. Okay. So what I was saying is that this shell model is a mean free model. So you have, say for example, late 209. Say for just I mean for making you understand. Now late is all those nucleons get paired up. Now if there is a 209 nucleons, that is one neutron extra. So that is unpaired. So what we do is that with these 208 nucleons, we make a potential, mean field potential. Now with that single unpaired nucleon, we just put that particle in that potential well. So the properties of that particular nucleon can be easily found out by solving Schrodinger equation, a particle in a potential well. Is it clear?
Yes, sir.
Is it clear? Okay, so then if you solve it, you arrive, basically you are quantizing the field, quantizing the problem. So basically you will get a series of quantum numbers. So that actually gives you to this, the leftmost part of the figure. Okay, so you will get for particular energy levels for particular quantum numbers. So that is the leftmost figure. And when you incorporate the spin orbit interaction, then you will get the rightmost figure. Clear? Is it clear?
Yes, sir.
Okay, so as you can see, I also discussed this shell model. It's we expect that there is close packing of the nucleons. We expect that the situation is B, that is random motion. But actually, the situation is A. So there are definite orbits just like atomic electrons. Again, it got disconnected, or can you see it?
Yes, we can see it.
Yes, sir. Yes.
Okay, so so actually the situation is A. You have definite orbits of the nucleons inside the nucleus, though it's close packing. Actually, Pauli's exclusion principle severely limits the possibilities for collision. That's why you have orbit picture inside the nucleus. So basically, if you get a mean field potential and you incorporate one nucleon in that particular potential, you quantize it. Basically, you solve the Schrodinger equation of a particle in a potential well, and you get the quantum numbers. Those quantum numbers actually tell you what are the different energy values where these particles can remain. So that gives you the leftmost figure. Now, to do that, you can see that this, if you solve the Schrodinger equation, you arrive at this capital N is equal to 2n plus L minus 1. You get it. Now this capital N is the number of the shell. Shell is what? How there are some energy levels which are close together. That thing we can call as shell. So you have this capital N that is equal to 2 times small n plus L minus 1, where small n is the quantum numbers, principal quantum number, and L is the orbital quantum number. So actually by solving Schrodinger equation you can get it. So now just this simple expression, n is equal to 2n plus L minus 1. This simple expression can give those energy levels. So how is it that? So first you consider the first shell, that is capital N is equal to 1. Now if capital N is equal to 1, let me take a piece of paper and I also solve it with you. If capital N, you also do it. Do you have pencil and paper with you?
Yes. Yes, sir.
Okay, so now you first write down the expression capital N is equal to 2 times small n plus L minus 1. Everybody do it. Capital N is equal to 2n plus L minus 1. Now you make a table. First you put what are the values it can take. So you take capital N is equal to say 1. That is shell number 1. If capital N is equal to 1 and you know the principal quantum number can take on value small n is equal to 1, 2 like that. So if capital N is equal to 1 and small n is equal to 1, then what will be the value of L? Can you tell me? Capital N is equal to 1.
Zero.
Where first
Zero.
we are considering shell number 1. So shell number 1 means capital N is equal to 1. If capital N is equal to 1 and you know principal quantum numbers can take on values 1, 2, 3, 4 like that. So if you put capital N is equal to 1 and small n is equal to 1, then what will be the L value?
0.
0. Excellent. So if L is equal to 0, then what will be the symbol of that? The symbol is L is equal to 0, orbital angular momentum 0 means it's an S shell. So it is S subshell rather, I would say. So it is a small s. And since the principal quantum number is 1, that is small n is equal to 1, you can write it as small 1s. So now you see the table. If capital N, that is it's in the figure that n is in a curly type of pattern as it's given in Cohen. So that n is equal to 1, you have L equal to 0, then you have 1s. Can you see that first symbol 1s?
Yes.
Yes.
So you cannot have any other value. You can consider small n is equal to 2, small n is equal to 3, but you don't arrive at anything. Okay, so it's only one solution that is available. That is capital N is equal to 1, small n is equal to 1, and L is equal to 0. Done? Okay, now let's go to shell number 2. That is capital N is equal to 2. If capital N is equal to 2, take first thing, small n is equal to 1. If small n is equal to 1, then what will be the L value?
One.
L equal to 1, right? So you can check that L cannot have any other value. Check it. If you take any other value, you cannot get a solution to that equation. Now, if L is equal to 1, capital N is equal to 2, small n is equal to 1, L is equal to 1. Now, if L equal to 1, it is a P subshell. SPDF, P subshell. So the symbol will be P, and since small n is equal to 1, it will be a 1P. So you see the second line, it is 1P. Can you see it?
Yes.
So now let's go to shell number 3. So that is capital N is equal to 3. Now if capital N is equal to 3, first you try with quantum number small n is equal to 1. If capital N is equal to 3, small n is equal to 1, then what will be the L value?
3.
3. If L is equal to 3, then it will be SPD. So it is a D subshell. So you get D, and since small n is equal to 1, so you write the 1 before D. So it is 1D. But there is another solution. If you put small n is equal to 2, if small n is equal to 2, then what will be the L value?
0.
0. So if it's a 0, then it's a S subshell. So you write a small s, and since small n is equal to 2, you write 2s. You got it? Okay? And you will see only these things are valid. Any other value of n and L you try to put, it won't be, you cannot do it, because it has to follow this equation. Capital N is equal to 2n plus L minus 1. Is it clear? Is it absolutely clear?
Yes, sir.
Now you see that capital N is equal to 1, 2, 3, all these number of shells. Now you go to this figure. So you have the first one, capital N is equal to 1. Now you see the leftmost levels. So you see in the leftmost level, you have capital N, the digits that represent on the right side, that is the shell number. 1, 2, 3, 4, like that. And the digits on the left side are the symbols that we just derived. So you have the shell number 1, you have only one value, 1s. Okay? Shell number 2, that is capital N is equal to 2, you have only 1p. Shell number 3, we just saw that there are two possibilities. So that is 1d and 2s. Similarly, shell number 3, like that. It goes on like that. There is one exception, that is 3a is there. So what happened that later on through experiments we found that there is another cluster there between 3 and 4. So we named it as 3a. Okay. So can you understand the leftmost figure now?
Yes, sir.
It is absolutely clear.
Yes,
Who asked me
Completely.
the levels that he did not understand, the shell model levels? Now who asked me? Is it Kaivalya who asked? Who asked?
Me, sir, Bhavani. Me, sir, Bhavani.
Okay. So do you understand it now?
Yes, it is clear.
It's clear. Now what happens when you incorporate the spin orbit into, now what happened in this S, you have two nucleons, that is 2 protons, 2 neutrons. In P, you have 4 neutrons, 4 protons. Like that. SPD, D, 6 neutrons, 6 protons. The occupancy is like that. Now what happens, for each orbital angular momentum L, you have spin up, spin down. So basically, if it's this P level, you have what is the spin multiplicity? You have 2 into half plus 1, like that. So basically, if it's L equal to 1, so what happened? This just a moment. You have this P level. P level can be broken up into 2 parts. Why? Because P is L is equal to 1. If it's L equal to 1, so it can take on value L plus half, L minus half. That is, L is 1. So 1 plus half is 3 by 2, and 1 minus half is half. So you have the P level actually composed of 2 levels, 1P 3 by 2 and 1P half. Is it clear?
Yes, sir.
Okay. So 1P 3 by 2 and 1P half. Now another thing is that, so that particular level 1p 3 by 2, how many nucleons can be accommodated in that particular level? That is determined by the spin multiplicity. So the angular momentum is 3 by 2, right? Total angular momentum, that is L plus half. So if it's 3 by 2, so 2 into angular momentum plus 1, that is 2 into 3 by 2 plus 1, that is 3 plus 1, that is 4. So 1p 3 by 2 will have 4 neutrons, 4 protons. And 1p half will be 2 into half plus 1, that is 2. That is 2 neutrons, 2 protons. So in altogether, in the P level, you have 6 neutrons and 6 protons. Is this clear? Absolutely.
Yes, it is clear now. So we have
Now,
something you said, L minus half to L plus half. For L equal to 1, we have from half to 3 by 2. And for each, I mean, for
yes.
half, we have 2j plus 1, 2. and for 3 by 2 we have multiplicity
Yeah,
4. So total
yeah,
6.
right. Total 6. So it is like this in the P level. Similarly, in the D level, you will see it can contain 10 nucleons, that is 10 protons, 10 neutrons. And the D level can be broken up into D5 by 2, D3 by 2, like that. So it is like that. So you have 10 nucleons there. So when you are given like in a shell model, tell me the levels. So you will write it from lower to higher. First level will be 1s half, next will be 1p3 by 2, then will be 1p half, then will be 1d5 by 2, then will be 2s half, then will be 1d3 by 2, like that. And you see these numbers, 2, that is 2 nucleons, and then it goes above, that is 8, like that. It goes on like that. So when you add up, you go to, for lead nucleus, you have to consistently you can put the levels, and you can feed up the levels with the nucleons, and you can arrive at the total number of nucleons in a particular nucleus. Now is this level structure absolutely clear now?
Sir, one question that why we have, I mean, first we had 1s half, then
Yeah,
we have 1p 3 by 2, then 1p half. Why it is that? I mean,
because of the energy level. Okay, so if you see in the energy expression, if you solve the Schrodinger equation, all these contributions will give you a certain energy level. So that energy level will be lower for 1p3 by 2, because there is a minus thing coming up, so it will be lower than the 1p half. Do you get me? So it is from the solution of the Schrodinger equation that this is energy wise, you plot it like that.
Sir, what is the main rule?
What
What is the main
what
rule?
is it?
Which energy level is lower and other is
Yeah, so you see it's, you will see that here this means that a given level nl will be split into two levels, nlj, with j equals l plus minus half, such that the separation between the levels is half into c into 12 plus 1. So one will be in the lower side and the other one will be higher. Okay, and maybe let's see if I have some expression
sir, how
that will be
can we
easier for you to.
differentiate between which level is
What?
higher? Sir, how
So
can we
it comes from the, yeah, I understand, but it comes from the solution of the Schrodinger equation. Now, if you solve in details, then you will ultimately get this solution, this picture. So now it is. I understand that you are not getting the feel because you have not solved it. So if you solve it, if you solve the Schrodinger equation, you will get the energy levels in such a way that will give you this picture on the right hand side that you are seeing. That because L does interaction, one will be a plus one, another will be a minus one. So the net difference between the two levels, basically one level is broken up symmetrically. So one level goes up, one level goes down. And in the energy expression, once you incorporate the spin orbit interaction, for one level it becomes minus, and the other level it becomes plus. The plus one goes up, and the minus one, that level goes down. Is it little bit clear now? You have to solve the Schrodinger equation to arrive at these levels, and it's not easy also. Okay, do you get my point?
yes, a little bit.
Hello?
For example, if we have two spin-half particles, the resultant could
Yeah.
be S is 0 or S equal to 1 total spin. And so
Total.
for S
Mhm.
equal to 0, we have a lower level, and for S equal to 1, which is the first, I mean a higher level. So for S equal
Yeah.
to 1, we had something like 1 by 4 h cross square, something like that. L dot S. Sorry, S1 dot S2, that coupling term. So that becomes higher,
Yeah,
and
actually, it is an, yeah, it is an L dot S coupling, and from that I am trying to see the expression. It should be somewhere. Let me see. There has to be somewhere.
uh, in
Let me see.
96 we have 96, I think we have
In
96.
page number
yeah.
96?
So you see, yeah. So you see this C into L dot S. If you put in the values of J, L, and S, ultimately you will see this level for the this lower one. It will enhance by half CL. It will go up, and the higher one, it will go down by minus half c into L plus 1. So ultimately, this spin orbit energy has a magnitude this. So because it is J equals L plus minus half, so for this case, you will see that a particular level will be broken up into two levels. One will go up and the other will go down. Okay, so one level will go up by half CL and the other will go down by minus half C into L plus 1. So that the net difference between the two levels becomes in the that expression that I said, half C into C whatever C plus 1, or what was that? So the difference is, yeah, half C into 12 plus 1. So the net difference between the two levels after they are broken up becomes half C into 12 plus 1. So this is, just a second, yeah. Okay, so where was I? Just a moment. Yeah, can you see it? Yeah.
Yes.
Hello.
Yes,
Yeah.
sir.
So what I was saying, that if one level is broken up, so what we are seeing is that the one level is broken up into two levels. So the net energy difference between the two levels will be half C into 12 plus 1. Okay, and this actually, where it is gone. Yeah. So you will see that one level will go up by half CL and the other will go down by minus half C into L plus 1. So that's the reason, and we are seeing that the 3 by 2 will go down instead of the half will go up. So if you have 1p 3 by 2, so there will be 1p 3 by 2 and 1p half. So 1p level will be broken up into two levels, 1p 3 by 2 and 1p half. So 1p 3 by 2 will be down by minus half C into L plus 1, and the 1p half will go up by half CL. Now what is your question?
Now it is clear, sir.
Okay, so technically speaking, you have to solve the Schrodinger equation to arrive at these levels. But first thing, if you consider only the n and L quantum numbers, so you get the leftmost figure. And then when you incorporate the spin orbit coupling, that is L dot S terms, then you see this breaking up of these levels into 2 or 3 or whatever levels. So some of the levels will go up and some of the levels will go down symmetrically about the original level. Now, any other question?
No, sir.
Anybody else?
No, sir.
So I plan to discuss a little bit about interaction of radiation with matter. I may not go in much detail because it may not pertain to your exam, this exam, but it is better to know it if anybody wants to continue nuclear physics in future career. So it is better to be taught this interaction of radiation with matter, because it is the fundamental concept for these nuclear detectors. So that's why it is very important. So I'll discuss briefly about it, and I will again address all your questions. Is it okay?
Yes, sir. Yes, sir.
Okay, so I have sent problem set up to 5, right? And solution set up to 4.
Yes.
Is it right?
Yes, sir.
So I will send a set of 5. I will send the solution set of 5 today, and the problem set of 6. On the last problem set I will send. And another thing is that you return me all the solutions, right? I think I have not got from everybody, because those are evaluated. And you will have internal marking for that. You understand? Okay. And so
Yes,
I will again reiterate that I would again tell that you go through the lecture notes and the problem sets very, very carefully. There may be short questions, short problems. So it is better to go through all these things very carefully. Just as I said, that first revision will take 7 days, next will 4 days, then it will 2 days, and then you will see that within 1 hour you can revise the whole syllabus. So that way you have to prepare. So then you will be, very comfortable with your exam. Practice again and again. You don't worry too much about too many problems. take selected problems, practice it again and again and again, so that you understand the inherent concept. Okay, so very limited number of problems, you practice very, very well. Clear?
Yes, sir.
Is it clear? Okay. Okay, then I'm signing off. Anybody has any other questions? And you also prepare for your gate very well. Okay. Okay, then I'm closing off. Okay, good luck. Okay.
Thank you,
Okay,
sir.
so next day,